Hello, and welcome back to Physics 141, Classical Electromagnetism 1. So, let's first review what we have discussed so far. So, in the previous lesson, uh, we have discussed about what happens inside a polarized object. So, there are actually bound charges. There are surface bound charges, and there are volume bound charges. And in the previous chapter, we have discussed about Gauss law for electric field. And it's basically equal to the volume charge distribution. So for this lesson, we will be introducing a new physical quantity called electric displacement. So the volume charge density rho that we have before in the previous chapters can actually be thought of as composed of bound charges plus the free charges. Where do you get bound charges? You get bound charges from a polarized dielectric or a polarized insulator. And where do you get free charges? You get free charges from conductors such as metals. So since conductors have free electrons, so they have free charges. So free charges can be seen in conductors. Bound charges can be seen in insulators or dielectrics. So the bound charges are actually due to polarization, and free charges are not whatsoever due to polarization. So if we go back to the original form of Gauss law, it's just the rho over epsilon naught, where rho is now equal to this one. So we can write it as this. And then, knowing that the volume bound charge density is just the negative divergence of the polarization, then we can write it as this. Grouping same terms or the same operation, you will notice that the divergence operation is now acting on this term here, where we can let this term here as our d, such that our equation becomes the divergence of d is equal to the volume charge density of free charges, where d here is our term that we in this parenthesis here, and we call that term as the electric displacement, and this equation now becomes a general form of Gauss law, which is the Gauss law for dielectrics. So actually, this is a more general form of Gauss law. It can be applied to objects that are polarized and objects that are not polarized. So if you will notice, the electric displacement D here is basically just an electric field, essentially. It's an electric field, but plus the polarization, plus P. Okay. So this is the differential form of Gauss law for dielectric. In terms of an integral, so using the divergence theorem, we can convert this to an integral. D dot dA is equal to the free charges, essentially. The analog of this in the original Gauss law is E dot dA is equal to Q enclosed over epsilon naught. But the permittivity epsilon naught is already within the electric displacement D. So note that if there are no free charges, it doesn't necessarily mean that there is zero displacement. It only means that if there are no free charges, it only means that the divergence is, there's no divergence in the displacement, meaning it is uniform or constant. Okay. So the electric displacement is an indicator of free charges. Again, free charges can only be in conductors, bound charges can only be in dielectrics or insulators. And there are systems which are a combination of those, a metal and a plastic, a metal and an insulator, for instance. So when you have that system, you can use the Gauss law for the dielectrics. Since there will be bound charges, there will be free charges in that configuration. So this will now be the boundary conditions for dielectrics. So similar with the electric field, there will be a discontinuity in the perpendicular component of the electric displacement at the boundary. And the discontinuity is actually due to the free charges at the boundary. Again, if there are no free charges at the boundary, the electric displacement is continuous, the perpendicular component. If you compare it with the electric field boundary condition, it's discontinuous. The discontinuity is because of the charge density, surface charge density sigma. Actually, there should be over epsilon naught here. Sorry, I forgot to. I had the wrong equation. So sigma over epsilon naught. Again, if there are no charges, whether bound or free at the boundary, then the electric field is continuous. Now, as opposed to the electric field, the electric displacement also is discontinuous. The parallel component rather of the electric displacement D is also discontinuous at the boundary. And the discontinuity is due to the discontinuity of the polarization. So if in the boundary, if the polarization is changing, if there's a discontinuity in polarization, then there will also be a discontinuity in the electric displacement. So as opposed to the electric field where the parallel components of the electric field are continuous, only the perpendicular components are discontinuous. Okay, let's have an example. So this is now a combination of a conductor and an insulator. So you have an insulated wire. This is your wire, current carrying wire. So of course, all of our wires are insulators. If you look at any wire in your home, at the core of it are copper, and then there's a rubber insulation or plastic insulation. So you have two problems here. Find the electric displacement inside and outside of a long straight carrying wire with line charge density lambda, with a coating insulation. So it's essentially inside and outside the insulation. And find the electric field outside the insulated wire. Okay, so let's start with letter A. So for letter A, to find the electric displacement, we use the Gauss law for dielectrics. And we will just use the integral form. So closed integral of d dot dA is equal to the charges enclosed by your Gaussian surface. You will still need to form a Gaussian surface here. So your Gaussian surface will be a cylinder because this is also a cylinder. So the charge enclosed, given the charge density lambda, is just lambda times the length enclosed by your Gaussian surface. So in this case, the electric displacement will just be the same at all distances from the wire, so it's constant, and then it will just become you can take it out of the integral, for instance, and the integral of dA is just the total area of your Gaussian surface. So your Gaussian surface here will be a cylinder, and the area concerned here is the area of the body of the cylinder. With the area of that is 2 pi RL, or in this case S, 2 pi S L, equal to lambda L. So from here we see that the electric displacement is just equal to lambda over 2 pi S. And from this case, assuming this is positive line charge, then the direction of this displacement is just S hat, radial. Okay, so this electric displacement is actually the same inside and outside the rubber insulation. So this is the electric displacement everywhere. So this is everywhere. Okay, for letter B, find the electric field outside of the insulated wire. So outside of the insulated wire, the polarization is actually 0. Meaning, from the formula of the electric displacement, it's just epsilon naught times the electric field plus the polarization. So if the polarization is 0 outside, then the electric field outside is just equal to d over epsilon naught. Essentially, the electric field is lambda over 2 pi epsilon naught s hat. This is just essentially the electric field of a line charge. So we cannot know the electric field inside because we are not given the polarization inside. And you cannot calculate actually for the polarization inside because we are not given what type of dielectric it is, what is the dielectric constant, and anything, any value related to the dielectric. Okay. So as a summary, these are our results. So another example is the field of a polarized dielectric shell. So this is a dielectric shell, but the shell has a thickness. So its inner radius is A, its outer radius is B. And there is a frozen in polarization within the dielectric shell because it's polarized. And the polarization in this case is radial. So this is the direction of the polarization. It's radial. And it depends inversely with R, meaning as R increases, the polarization decreases. Okay. So for the first question, you are asked to locate all of the bound charges. Okay. So there are only two surfaces where there will be bound charges here. The inner surface and there's the outer surface. So there's two surfaces. And then there's also the volume of the sphere. Okay. Sorry, yeah, volume of the shell rather. So with this, we can say that there will be negative charges in the inner surface because of the direction of the polarization. There will also be negative in the volume, and then there will be positive charges at the outer surface. So that is the picture of the charge distribution here. Okay. So let's first locate the bound charges. Let's start with the surface charges. Sorry. So let's start with the first surface. R is equal to A. So at R is equal to A, it's just the polarization that with n hat evaluated at R is equal to A. So the polarization is just K over R hat. And what is n hat? This is very tricky. N hat is always perpendicular to the surface and it's out of the surface. In this case, n hat is actually going to the center. That is n hat for the R is equal to A surface. For the R is equal to B surface, this is actually n hat. So n hat is always away from the surface or away from the volume. So that's the definition of the n hat vector. So in this surface here, R is equal to A, n hat is actually negative R hat. It's towards the center. So you evaluate this at R is equal to A, and you will get negative K over A. You do the same thing for R is equal to B, and you will get K over B. Because n hat here is positive R hat. So it's positive K over. So this will now be our, as a summary, this will now be our bound charges at the surface. It's negative K over A at the R is equal to A surface and positive K over B at R is equal to B surface, at the outer surface. So initially confirming our initial assumption here that there will be negative charges in the surface and positive charges at the outer surface because the direction of the polarization is outward. And the polarization is always directed from the negative to the positive charges. Okay, how about the volume charges? So in this case, it's just negative the divergence of the polarization. So for the divergence, we only take the R component of the divergence operation. So 1 over R squared partial with respect to R of R squared times the R component of the polarization. So the polarization is purely R component, K over R. So doing that one, this will give us a volume bound charge density of negative K over R squared. So this bound charge is within the volume. So you will notice that as R is inversely proportional, as R becomes greater, as R becomes near the outer surface, the density becomes smaller actually. So there will now be very small volume charge density at the surface. So yeah, so no more because at the outer surface it's now positive charges. Okay. So we now have located all of the bound charges. So let's now proceed to the second problem. For the second problem, we are asked to find the electric field everywhere using Gauss law and the result in A. Okay. So in this case, we actually have three regions here. This region from 0 to A, this region from A to B, and this region from B to infinity. Okay. Obviously, in region 1, the electric field in region 1 is 0 because there is no charge enclosed here. Now, for region 2. So, for region 2, we again use Gauss law. So, we use the original Gauss law. The E2 dot dA is equal to Q enclosed over epsilon naught. So, what is the charge enclosed in region 2? So if you'll notice in region 2, there will be surface charges in this surface, and there will also be bound charges. So in region 2, the charge enclosed will be due to the bound charges, sigma dA, plus due to the volume bound charges, surface bound charges and volume bound charges, rho dV or rho d tau. So this is, okay. So from our previous result, this is just the bound charges, surface bound charges at R is equal to A. And the value of this is negative K over A. So from our previous result, we also have obtained the volume bound charge density, and this is just equal to negative K over R squared. And the differential volume, since there are no theta and phi dependence, theta and phi dependence, it's just 4 pi R squared dr. Okay, so since this is constant, we take it out of the integral, and it's just the total integral of dA, which is the total area of our Gaussian surface. So it's 4 pi R squared in this case. Or sorry, total area of our surface, where our surface is this surface here. Take note, this is a surface integral, and the surface that it's talking about is this surface here. R is equal to A. So the integral of dA here is 4 pi A squared. So you will get negative K over A, 4 pi A squared, and from this integral here, you will get 4 pi K R minus A. So the charge enclosed will be negative 4 pi K R. So this will now be negative 4 pi kr over epsilon naught. So similarly, you can take it out of the integral. This will just be constant, and you will have just E2 times the area, which is 4 pi r squared. And you will get E2 is equal to negative k over epsilon naught r. And since we know or in vector form, this is the direction of this is actually negative r hat, because it's negative charges. So the electric field, the charge enclosed inside is actually negative, as we have presented earlier. There will be negative charges in the surface. There will also be negative charges in the volume. So the electric field direction is negative r hat actually. Now, for the third region, the region outside of this sphere, you will actually need to solve for the total charge enclosed by all surfaces and the whole volume. So for region 3, the charge enclosed will be the bound charge, surface bound charge, this is at r is equal to a, plus the bound charge at r is equal to b, plus the volume charge. And if you add all of that, you will actually get 0. Hence, the electric field at region 3 will be 0. So I will leave the rest, these calculations to you. But you have already shown this earlier in the previous lesson, wherein if you have a frozen polarization, when the dielectric is initially neutral, actually it should be initially neutral, and you polarize it, the charges will just redistribute, but the total charge is still neutral or 0. So that's what happened here. So this will be our result for letter B. So for the third problem, we are asked to find the electric field everywhere, but now using the electric displacement D. Okay, so we will use the Gauss law for dielectrics in integral form. So this one. Now, in this case, we don't have conductors here. This is a dielectric shell, meaning there are no free charges because there's no free, there's no conductors here. Only conductors have free charges. So in this case, 0, meaning your dielectric is, electric displacement is 0. So from the formula, since this is equal to epsilon naught E plus P, so this implies that for the region here, region 1 and region 2, in region 1 and region 2, the polarization is actually 0. So this is 0, meaning the electric field E1 and E3 will also be 0, since the polarization is 0. So electric field must also be 0. Now in region 2, sorry, this is region 3. In region 2, we are given a polarization. The polarization is actually this one, K over R hat. So therefore, from this equation, we work out from this equation, given the polarization, we can solve for the electric field in region 2. Will just be equal to the negative of the polarization over epsilon naught. And it's exactly equal to negative K over epsilon naught R hat, which is the electric field that we have obtained using Gauss law, the original Gauss law. So you will notice that the electric displacement, the Gauss law for dielectrics, a much more general way for solving problems, especially if it involves dielectrics. So this is the summary for this problem. These are the location of the surface bound charges. And these are the electric field. And region 1, region 2, and region 3. And for letter C, the electric displacement is 0. You will still obtain the same values for the electric fields in all the regions. Okay, let's now go to a third example. So a polarized sphere with a cavity. So you have a polarized sphere. So initially, this is the polarization P. Initially, it has an electric field E sub 0. So this is a polarized sphere with a cavity. So initially, this is the it's a whole sphere. And then you carve a cavity at the center of the sphere. So the question now is, find the electric field at the center of the cavity in terms of the original electric field and the polarization P. And for letter B, find the electric displacement inside the cavity in terms of the original displacement and the polarization. So the original displacement, electrical displacement in this case, will just be epsilon naught times the original electric field without the cavity plus the polarization. This is d naught, the original displacement. And you're essentially asked to find the electric field and the displacement inside the cavity. Okay. In order to solve this problem, we will treat this problem as a superposition of two polarized spheres. But the other sphere is just smaller. Actually, in fact, it has the same size as the cavity. And the polarization in this smaller sphere is still P, but it's directed in the opposite direction. Essentially, in this region here, the superposition in this region here, the polarization is actually 0. Inside the cavity, since there's no dielectric inside, there's no polarization. There's nothing to polarize if there's no dielectric. So essentially, it's a superposition of a large sphere and a small sphere with opposite directions of polarization. The same magnitude but opposite polarization, causing the overlap region, the superposition region, having 0 polarization. Essentially, that's how we will solve this problem. Okay, so to solve for the electric field in the cavity, it's just basically the original electric field minus the electric field of the cavity. The electric field of the small sphere minus the electric field of the small sphere with the opposite polarization. And we already have solved for the electric field of a polarized sphere. Essentially, this is just equal to negative P over 3 epsilon naught. So this electric field is actually directed upwards, negative of the polarization. Since its polarization is downwards, the electric field is actually upward. This is actually upward. And the original electric field is actually directed downwards because it's opposite the polarization. It's negative P over 3 epsilon naught. So in this case, the electric field now at the cavity, just E naught, the original electric field, plus the polarization over 3 epsilon naught. So that's it. That is the electric field at the cavity. How about for the electric displacement? So the electric displacement will just be equivalent to epsilon naught times the electric field at the cavity plus the polarization at the cavity. In this case, there is zero polarization at the cavity, so plus 0. So just multiply this by epsilon naught. So you will get epsilon naught E naught plus P over 3. So we will write this in terms of this one. So from here, we see that P is just equal to D naught minus epsilon naught E naught. So we can actually write this displacement of the cavity in terms of D naught and P. So in terms of D naught and P, the original displacement is D naught minus 2/3 P. Okay, so easy peasy. So it's easier to analyze a problem using by treating it or looking it at another angle or another point of view. Similar with what we did in the previous chapter, wherein we treated a uniformly polarized cylinder or sphere, for that matter, as a superposition of two spheres of opposite charges. Okay. So that's the end of this lesson. So in the next lessons, we will be trying to formalize what is the relationship between the electric field and the uh, polarization. So I will see you again in the next meeting.